Alrighty, so this is the start of section 7.4. We're going to talk about a new method of integration called partial fractions decomposition. So this should be new for just about everybody, if I had to bet. I don't think they teach this in, if you do a calc course in high school. I don't think this usually is something that gets covered. But so the big idea behind partial fractions is this. So let's first note that, if I had two fractions here, so 2 over x minus 1 minus 1 over x plus 2. And, you can do a common denominator. But when you work that out, you're going to get that, when you put these over a common denominator, x squared plus x minus 2, you're going to get this. So you can, if you have two of these rational functions, you can always, find a common denominator and write them like this. So the question becomes, if I had this integral, if I had this integral, it might not be something that is easy to do with u substitution. U substitution might not be possible here. It probably is not. Yeah, probably not. So the question becomes, how can I do this? Well, sorry, this is supposed to be an x plus 2 up here. Let me erase that. So if you're asking yourself, how do I do this integral? The answer is in the line above this. I could, split this up into two integrals. So I can split this up as this. And so I could split this into two integrals, and those two integrals I know how to do. So this is the integral 2 over x minus 1 dx minus the integral 1 over x plus 2 dx. This would be 2 times the log of x minus 1 minus the natural log x plus 2. So if I'm handed something that looks like, this, a rational function x plus 5 over x squared plus x minus 2, if I were able to split this up, if I knew how to split that up, it would make doing the integration much easier. And so we're going to get to that, but first, so that's the idea behind partial fractions decomposition. We're going to talk about how you can take something that looks like this and turn it into something that looks like that. So let's start with polynomial division first. So you'll remember, so polynomials, they're like they're just additions of powers of x. So like x plus x squared, positive powers, positive integer powers. We all know what a polynomial is. So what that, if you can imagine, in terms of that variable, that thing represents a number. So if I had, a polynomial, two polynomials, p of x divided by q of x, so just like I can do division with rational or with fractions, so like 7 divided by 3, I can compute that with long division. I can do the same thing with polynomials. So the idea is if the degree of p of x is greater than the degree q of x, so we're going to do greater than or equal to, then I can write p of x divided by q of x is equal to s of x plus r of x divided by q of x. So think about this in terms of like dividing numbers. If I had like 7 divided by, if I were going to do 7 divided by 3, I could write this as, so it's going to be 2 plus 1 over 3. And this is all that is. So this corresponds to the number of whole times I can divide into this. This r of x is the remainder, and q is the quotient. So that I can do the exact same thing with polynomials. And I'll do the first example I have here is going to be an integral we have to do with polynomial long division. So we'll get a recap of how to do it there. So I know there's synthetic division. I'll be completely honest. So I've seen it. I've seen it. I've never took the time to learn it just because I can never actually remember when you're allowed to use it. So for me, it's easy to remember polynomial long division and not have to rely on synthetic division and run across a case where I can't use synthetic division. So I'll do this by all of these by polynomial long division. You can use synthetic division, great. It's the same thing. It just gets rid of some of the information that's not needed to do it. But anyway, so let's jump into our first example. So we're not yet to partial fractions. This is just doing these things with polynomial division. So we have the integral x cubed plus x divided by x minus 1 dx. And so you can see here the degree of the numerator is 3, the degree of the denominator is 1. So because the degree of the numerator is larger than the degree of the denominator, we can do this division and get something that looks like s of x plus r of x over q of x. So let's do this division. So the way you do polynomial long division is the lower degree one goes outside. I'm going to divide into x cubed plus x. And now it's just like regular division. I ask myself, okay, what do I multiply x by to get x cubed? That's going to be x squared. So then x times x squared is x cubed. Negative 1 times x squared is minus x squared. I'm going to subtract this. That way the x cubes cancel. And now I just subtract, terms of the same thing. So I have, a 0x squared up top. So I get, a negative x squared. So I get a positive x squared down bottom. And then x, so yeah. So, and then plus x up here. And then minus 0, because there is no term in the x. There's no x term in the bottom one down here. So I just get x squared plus x for that first round of division. And I keep going until the degree is less than the degree of this one. All right, so now I ask myself, what do I multiply x by to get x squared? Because now I'm looking at this, and I'm looking at this. So what do I multiply x by to get x squared? I'm going to multiply by x. So x times x squared is x squared. Negative 1 times x is minus x. I'm going to subtract these again. Just like before, those cancel. That's what we expect. Now we have x minus negative x. This is 2x. And now I just keep going. Now I'm looking at this and this. So what do I multiply x by to get 2x? Well, I multiply it by 2. So I do a plus 2 up there, and then I just do the multiplication. 2 times x is 2x, minus 1 times 2 is minus 2, sorry. I'm going to subtract these. So again, these cancel just like I want it to. Now I have a negative 2, so that's a positive 2. And I have to stop here. So the degree of 2 is less than the degree of x minus 1, so I stop. And now I can write, this. I can write, so the whole point of that is x cubed plus x over x minus 1 is equal to the quotient here. So x squared plus x plus 2, and then the remainder plus 2 over the thing I'm dividing by. So it's, you write, if you have this, so if you have x cubed plus x divided by x minus 1, it's going to be this plus the remainder divided by the quotient there. And now you can see that, this is an integral I can do. So I have that the integral x cubed plus x over x minus 1 dx is equal to the integral of x squared plus x plus 2 plus 2 over x minus 1 dx. And now I can just integrate that. So I'm going to get x cubed over 3 plus x squared over 2 plus 2x. And then this last one, it's a logarithm. So this is 2 ln of the absolute value of x minus 1. If you're not seeing that, just, separate everything. If you have to do u substitution, that's fine. Eventually, you should get to the point where you look at this and you say, okay, that's a logarithm. So, if you were on an exam and you just went from, this line to this line, that would be fine. As long as I can understand, it's obvious to me that follows from that directly. And then don't forget your plus c. So this would be your final answer. So that was an example of, it wasn't partial fractions, but we had this integral here, x cubed plus x over x minus 1. We weren't able to do it with the u substitution or integration by parts. So what we ended up doing was we ended up saying, okay, I can do polynomial long division. And when I did that, it gave me this, which is easier to integrate. And so I integrated it and got my final answer. So I'm going to stop this video here. So in the next part, we're going to actually get to partial fractions. We need to see this because, there are some integrals where you might have to do polynomial long division in order to figure out, or in order to get something that you can actually integrate. But the real, main part of this chapter is going to be partial fractions. So let's stop here.